Hello viewer, welcome back to my channel. This is Dr. Dorcas NGIGI. We are moving on with our topic of uniform circular motion. So this is our fourth topic. This is our fourth lesson. Now in today's lesson, we're going to look at something new. We're going to look at what we call acceleration, centripetal, okay? So we're going to look at centripetal acceleration. Now, anytime we talk about acceleration, it means that the velocity, of course, first there is a velocity, and for the acceleration to come in, then this velocity must be increasing with time. Okay, so when the velocity is increasing with time, then we see that a body is accelerating. Okay, if the velocity of a body is decreasing with time, then we say a body is decelerating. Now in circular motion, we have a body moving on a circular path, but it moves on a circular path with constant speed, not constant acceleration. Now the reason is, if it is moving around the circular path at 2 meters per second, the speed from that point all the way back to the same point, the speed will continue to be 2 meters per second. So it goes around the circular path at constant speed. Remember, speed is a scalar quantity. Speed is a scalar quantity, meaning speed has only magnitude but no direction. Okay? But we have velocity, which is a vector quantity. And by vector quantity we mean velocity, besides the magnitude, it also has a direction. Now when a body is moving on a circular path, yes, it's true, it moves at constant speed, but the velocity is not constant, because velocity is a vector quantity. Now when a body is at point, like for example, when the body is at that point, then it is moving. If you were to release it, it would move along the tangent. Okay? So if I call this point A, then the velocity is in that direction, assuming the body is moving in the anti-clockwise direction. If that body comes to this point here, let's call it point B, then the velocity again will be along the tangent, and I call that VB. Okay? Now, VA and VB have the same magnitude, 2 meters per second, but different directions. And because they are different, then of course they are going to be different even in terms of, those are two different velocities. Let me draw this diagram. Let me draw it here. There's a circular path. So a body at point A is moving along the tangent with VA, and when it comes to point B, it moves along the tangent with VB. Now VA is not equal to VB. Yes, it's true, the magnitude of the two are the same, but the fact that they have different directions means that they are two different velocities. Let's go to Newton's first law. In Newton's first law, we say a body should continue in the same state of rest or motion on a straight line unless it is acted upon by some external force. That means that for the velocity to change from direction A to direction B, there has to be some force applied. Okay, so a body cannot change its direction if there is no applied force. Now the question is, what is the direction of the applied force? Now for a body to move in direction A, then the force is in that direction, VA. Okay, VA. For a body to move in direction B, there has to be force VB in that direction. So anytime you apply some force, that force will cause a body to either change velocity in terms of direction or to change velocity in terms of magnitude. Okay, but in circular motion, the magnitude does not change. The magnitude, if it is 2 meters per second, the force does not change the magnitude. What it changes is the direction of the body. But either way, the velocity has changed. Now, this is the center of the body. Let's call it that center R. From the center to where I have point A, let's say that is point A. If you look at the two, they are making 90 degrees. The direction of velocity A and the radius R are making 90 degrees. So we can as well say that the radius is normal to. A normal is a line that cuts another at right angle. We call it a normal. So the radius here is normal to VA. Now if we come to point B, if I want to draw a normal, I'll draw a line coming from the center to connect with point B. So again, that is 90 degrees. So the radius is still normal to that. If the angle between the two radii is theta, okay, so the angle between the two, if I were to produce this normal to touch the other velocity like that, that angle will also be theta. Let me explain. Because this is a normal to the first radius, and the second velocity is a normal to the second radius. So if from one radius to the other you have moved an angle clockwise, anti-clockwise, an angle of theta, then to move from the first normal, the normal of the first radius, and to go to the normal of the second radius, you'll have to move the same angle theta. That's very important to note, that this normal and this normal, the angle between them is also theta. Why? Because VA is a normal to R, and this VB is a normal to the second R. So to move from the first R to the second R, if the angle is theta in the anti-clockwise direction, then to move from the normal of the first R to go to the normal of the second R, you have to move the same angle theta. That's very important, and that we saw in when we are looking at plane mirrors. Okay. Okay, now with that, then it means what is constant here. Now, velocity has the vector part, is a vector quantity, so it has the constant part, which is the speed, and it has the changing part, which is the direction. So if I take this triangle, if I take this section here, and I call this delta S prime, okay, what is changing there? R is constant. R is the radius of the circle, is not changing, but the arc length is changing. Remember, if this R were here, that would be the arc length. When it is here, that is the arc length. So when talking about change in S prime, we are talking about change in arc length. Now what is changing in this triangle here, if I were to put that, what is changing there is the velocity. What is constant is the speed. So if I were to redraw this triangle here, then I would draw it like this. We'll have that as my delta V. Why delta V? Because velocity is changing because of change in direction. But what would be the same? What would be the same is the speed. Velocity has two parts. It has the direction. We are changing from VA, from A to VB. So there is delta V. From VA to VB, VB minus VA is delta V. But the speed is constant. The speed part is constant. And this angle is theta. Is this angle here, theta. So the speed is the same, but the velocity A and the velocity B are different. So that is what we have here. The speeds are the same. Theta is this angle, but delta V from VA to VB, that is delta V. Velocity is changing because of change in direction. Now, if we compare that triangle to this triangle here, if I call this point C, A, we call this point B, so CAB. Of course, you know we can draw here like that. So A to B. But what I'm interested in is this, assuming there's no much difference between this arc length and that line AB, assuming the difference is very small, then we can say that this triangle here, CAB, and this triangle here, let me call this C prime. So CAB and C prime, let's call it this C prime OP. So let's say the triangle CAB is similar to the triangle C prime OP. Okay? And if they are similar, then it means this arc length here, delta S prime, divided by delta V, which is change in velocity, remember velocity is not constant, should be equal to what is constant, CA is our radius, divided by what is constant here, C prime O is our speed. Okay, don't get confused. Speed the S prime is the arc length. Okay. Okay, so with that, these triangles, because they are similar, triangle CAB and triangle C prime OP are similar, then since they are similar, then this side divided by this side should be equal to that side divided by that side. Now, delta V is our velocity, so we can make it the subject. So if I multiply by delta V both sides, then I get delta V will be equal to delta S prime, delta V times delta V times S over R. Okay, I'm just rearranging the equation so that delta V becomes the subject. Okay, and remember, delta V is a change in velocity because velocity is not constant, it is changing. But S is our speed, the speed on the circular path, that one is constant, so it's not changing. So R is constant, S is constant, but V is not constant, so we have delta V. S prime is the arc length, is also not constant because as the body goes round, the arc length also changes. Okay, now in that equation, I want us to divide both sides by delta T. We'll see why. So delta V over delta T will be equal to delta S prime multiplied by S over R delta T. Okay, but delta V over delta T, that is change in velocity divided by change in time taken, that is acceleration. So delta V over delta T equals to acceleration. So acceleration equals to what? It is delta S prime over delta T multiplied by S over R, this part here. But if you take a good look, from A to B, delta S is a length. It is the arc length. Okay? So change in length, that arc length, divided by change in time, that is speed. Change in distance divided by change in time taken, that is speed. So we can say that this is speed times S is also another speed over R. So we can say acceleration is S squared over R. Where S now, pay attention, S is the constant part, 2 meters per second, which the body is going round with. So it is that S squared over R. But for purposes of our working out, we can take that S as V squared over R. But always remember, V, velocity, is not constant. it is the speed that is constant. And so the acceleration in a circular path is simply v squared over r, or simply s squared over r. Why s? Because the speed round the circular path, that one is constant, but the velocity is not constant because the direction of the object keeps on changing. And so we have derived the equation for acceleration. Okay, so a body moving around a circular path accelerates. Yes, it's true, the speed might not change, but the fact that the direction changes means that that body is accelerating, even though the speed along the circular path is constant. That's number one. So acceleration does not have to do with the change in magnitude or velocity. Acceleration has to do with if the magnitude changes, the body has accelerated. If the direction changes and the magnitude does not change, still the same, the body has accelerated. So change in acceleration in circular motion has nothing to do with the change in magnitude of the speed. It has to do with the change in direction of the object. And from the Newton's first law, a body cannot just change its direction. For the direction of a body to change, even though the speed is constant, there has to be application of some external force. So in our next lesson, we are going to look at what we call centripetal force. Because for there to be centripetal acceleration, there must be some centripetal force which causes that acceleration. Okay, so that brings us to the end of this lesson. I hope you enjoyed the lesson, and I hope you're going to take your time to go through what we have learned so that you get better understanding of this, this lesson. Don't forget to like, subscribe, but most importantly, to share with the people you know will require this knowledge. Until next time, goodbye.